Hello everyone, in this video we'll try to discuss one of the three important derivations in the module number 5, which is centrifugal pump. So in centrifugal pumps, which is module number 5, we have three important derivations over there. Number 1 is relation between H and the flow. Relation between H and the flow. The second one is the minimum starting speed of the centrifugal pump, and the third one is the pressure rise in the centrifugal pump. So these are very important derivations. So totally you have three derivations to be understood in this particular module. So we'll try to cover one by one. In this video, we'll try to cover the first derivation, which says the relationship between H and K, the head and the flow. What is the relationship between the head and the flow? We'll try to cover in this video. So before going to the in-depth about the derivation, we'll try to understand the three different veins that happens to be in a centrifugal pump. Veins are nothing but the blades of an impeller. So basically there are three different veins. The first one is backward vein. Backward vein, I can see in the above figure. Second one is the forward vein. Forward vein, and third one is the radial vein. So only these three varieties of vein are there in case of an impeller of a centrifugal pump. So the velocity triangles for all these three veins would be different. However, the input to a centrifugal pump is a radial thing, therefore input velocity triangle would be something like this. V1, because it is radial, V1 would be equal to Vm1, and this is Vr1, where your alpha 1 would be equal to 90 degrees as it is going inlet. Okay, so this is nothing but your beta 1, and this becomes your U1. So this particular inlet velocity triangle is same for all the three types of the blades. That means for all the three types of blades, the input is the radial, but the output is different depending upon the type of the veins used. For example, if it is a backward vein, then how could be the velocity triangle? The velocity triangle would be something like this. I'll just shift the things up here. This is a backward vein. What am I? Okay, so if this is a backward vein, the velocity triangle would be something like this. It would go like this, and this would be your VR1, the outlet, VR2, this is VM2, and V2 would be somewhere here. This is alpha 2, and this is beta 2. This is VU2, and this becomes your U2. So this is the velocity triangle in case of a backward vein. Now, what would be the velocity triangle in case of a forward vein? Let us see now. Anyhow, the input velocity triangle, as I told you, would be same for all the three veins. Okay. Okay, now for the forward vein. So as you describe a vein, the outlet would be something like this, which is VR2, same thing. Okay, and something like this. VR2 will come in middle. Okay. Now, so this becomes your V2 and VM2. This is beta 2, alpha 2. This is U2 and VU2. So this becomes your velocity triangle in case of forward vane. So what is the difference you can observe? In case of backward vane, it is a isosceles triangle. In case of a forward vane, it would become something similar to a equilateral triangle. So this you have to remember. I guess you can hope what would be the velocity triangle in case of a radial vane. Radial vane, in the sense as the name describes, the outlet would be radial. So whatever the outlet is coming from this end, it would reach here and form a velocity triangle like this. So this becomes your V2. Of course, this is VR2, which is equal to VM2 since it is radial. And here you have to observe that U2 would be equal to VU2. This is alpha 2 and radial outlet, therefore beta 2 is 90 degree. So in order to solve the problems on the centrifugal pump, these three velocity triangles are very much important. Number one, how would be the velocity triangle in case of a backward vane, and how would be the velocity triangle in case of a forward vane, and how would be the velocity triangle in case of a radial vane. So if you know these three, the problems and all the theoretical concepts would become rather very easy. Okay, so now let us jump into the derivation. Okay. Now, you know that this is the derivation of Theriotical head capacity relationship. So theoretical head capacity relationship we will try to derive now. Generally, the energy from a turbo machine as per Euler's equation is given by U1 VU1 minus U2 VU2, correct? Now, since pump is a power absorbing machine, what you can observe is U2 VU2 would be greater than U1 VU1. Okay, since this is a power absorbing machine, therefore it is rather easy for us to write U as U2 VU2 minus U1 VU1. Why you are changing this particular pattern? Since this is a power absorbing machine. Now, velocity triangles, we shall consider the backward vane and draw a velocity triangle. Okay, like this. For a backward vane, I'll just copy that. That would be better, I guess. Okay. So this is a velocity triangle. I'm picking this up now. Okay, in order to solve the derivation. Okay. Right. Now, from this, E is equal to U2 or VU2. Remember, the energy developed here is nothing but the head developed. So what I will take this as nothing but the value of H, which is equal to U2 VU2. And why I am not taking U1 VU1 is we are assuming no Vril component at inlet. So as we are assuming no Vril component at the inlet, VU1 becomes 0. So from this, from the above figure, operate tan beta 2. Tan beta 2 is what? Opposite by hypotenuse. Opposite by adjacent. opposite is Vm2, whereas the adjacent is U2 minus Vu2. From this, what can I write as U2 minus of Vu2 would be equal to Vm2 divided by tan beta 2. Okay, or else Vu2 is equal to U2 minus of Vm2 into cot, because 1 by tan is cot beta 2. Fine. Now, we all know that volume flow rate is given as Q is equal to A into V. Okay. Now, in this particular aspect, Q is equal to A2 into Vm2. Now, from this, Vm2 is what? Q divided by A2. Now, you have the value of Vm2 and you have the value of Vu2. Let us try to incorporate these two in that particular equation. So, taking this as something like equation 1. Okay. Now, I will take this as equation 2 rather. The above one I will be taking it as 1, which is this one. Okay. Now, so from this, substituting there, Vu2 is equal to U2 minus of Vm2 is what? Qf divided by A2 cot beta 2. Qf divided by A2 cot beta 2. Okay, so now substituting the value of Vu2 in equation 1. So what happens there? H is equal to U2 square minus U2 into Qf divided by A2 into cot beta 2. So this is what happens when you substitute the value of Vu2 there. Now, this can I write it as K1 minus Q times of K2, where K1 would take U2 square and K2 would take U2 divided by A2 into cot beta 2. So this is the relation what you expect to be written in case of question asked on theoretical head capacity relationship. So this is the relationship of theoretical head capacity. It correlates the head with the flow using these two constants, where K1 is equals to U2 square and K2 is equals to U2 divided by A2 into cot beta 2.